So now that we've talked about matter, matter is made up of, for purposes of this course anyway, 3 particles. We have protons and neutrons in the nucleus of an atom, and then we have electrons in a cloud outside the atom. Okay, and we said that atoms or matter can interact with incoming light or energy different ways. Okay, we said that that light can be absorbed, that light can be transmitted, or that light can be scattered or reflected. And remember, when we talk about light, we can talk about different forms of radiation. For instance, we could talk about what happens with gamma rays when it interacts with matter, what happens with radio waves when they interact with matter. Okay, so we're going to talk about this thing called spectral lines. And spectral lines has to do with the electrons. Specifically, spectral lines are created as electrons change energy states. Now, these little lines I'm showing you here are different energy states, and it's kind of, think of it as kind of like along this y-axis we have increasing energy. Okay, so basically I can have an electron down here at this energy, what we call this energy state, and I can zap it with energy, and it will be promoted up to a higher level. Now, look, I skipped a level, didn't I? It can happen. And then when that electron falls back down, it will release energy. And the amount of energy it took to get excited to that higher energy level is equal to the amount of energy that will be released when it falls back down. Okay, this is what we call transitioning different energy states. So just generally speaking, my understanding of a light bulb, okay, light bulbs are filled with a gas. And of course that gas is made up of atoms, and around those atoms in the clouds are electrons. Basically, when you turn on a light bulb, you send a surge of electricity, okay, that it will excite electrons that are in a cloud. It'll excite the electrons that are in a cloud outside the nucleus to a higher energy state by electricity, and then as they fall back down, we see the light. Okay, the light is emitted as those electrons fall back down. Isn't that cool? Okay. Well, what does this have to do with astronomy? Well, our cosmic messengers actually send us information transitioning. They send us from those cute little electrons so far away in the matter that's making up the stars or making up the nebula, or making up the galaxy. They send us cute little discrete packets of energy information. Either electrons are absorbing energy and we see that, or electrons are emitting energy and we see that. They're either being excited or falling back down to their ground state. So, and we can deduce then the chemical nature of those distant celestial objects. There you go, in a nutshell. So Kirchhoff came up with, I'm not sure the background here, but there are what we say 3 of Kirchhoff's laws. Now, this first law basically says that we are going to see all colors of the rainbow, Roy, G, Biv, without interruption. Basically, think of this as we have electrons. This will work. Okay, here again, think of these as my energy levels that electrons can hang out at. Think of, we have all possibilities of transitions, and they are all falling down. Okay, so we got an assortment of energies being released, and you end up with a complete rainbow, no breaks. Okay. Then enters this idea of emission lines. Emission lines are sometimes called bright lines or bright line spectra. And I like the name bright line spectra because that's what they look like. They look like bright lines against dark colors. And if you think of, I'll draw my energy levels again. Bright line spectra are always created from excited electrons that are excited states Remember, this is my energy diagram, energy increasing. Electrons have been excited and they're falling back down and they emit a little bit of energy or light. Okay, and this distance right here, they fall back down, is a particular color. Okay, so bright lines, that's a bright line spectra. Electrons have been excited, they fall back down to ground. Okay, and in a excuse me, and in a light bulb we see all different colors, right? Well, absorption line spectra look at that phenomenon by which electrons, let me go ahead and draw another energy diagram here. Okay, absorption line spectra are sometimes called dark line spectra. I like that, it's very descriptive. Spectra, okay, this should be an A. And what's happening with dark line spectra is it's the transition of an electron from, this is increasing energy. It is basically looking at this phenomenon where an electron hanging out at a lower energy level gets a certain amount of energy and is promoted upwards. Okay. So what we're looking at here is kind of the energy that's being absorbed to be promoted. Okay, so basically then what you'll see is a continuum, and you'll see a bright, this is all bright colors of the rainbow, and then you'll see these dark lines, and these dark lines correspond to the energy that was absorbed. Okay, and so emission lines and absorption lines for the same compound or element will be identical. They're like negatives of each other. And they are like fingerprints. This is how we can understand the chemical nature of celestial objects. Oh, it's a little bit messy over here. But Kirchhoff's law 1 is the continuous spectra, no lines. Kirchhoff's law 2 would be those emission lines or bright line spectra, where electrons are falling back down from excited states. Kirchhoff's law 3 would be the absorption lines, or the dark lines, where you have a rainbow and you see some colors are missing because those colors have been used to excite electrons to a particular, to an excited state. So these spectral lines, whether they're absorption lines or emission lines, are characteristic of an element or compound. So this is kind of a, this is showing us in two different ways. This is showing us what we call spectra. Okay, this line right here, you can probably see kind of the violet over here and the red over here. So this would be what, longest wavelength, and this would be shortest wavelength here anyway, of color, visible light. And so notice that it's got a few features, and we'll talk about these. Do these look like the absorption lines, Kirchhoff's law 3? They are. And these are trying to kind of show you bright lines against a dark background. So these would be emission lines. Now, the same information is presented graphically here. So notice that graphically, and usually instead of the word ultraviolet, it will have either the wavelength or the frequency for that color. And then, of course, we have blue, green, red, getting longer wavelength. On the other side of red, we have infrared radiation. So these are wavelengths. Again, longest wavelength down here, shortest wavelength here. And then along the y-axis for the graph, we have intensity. So notice, for instance, if we kind of focus on these lines right here, they appear as kind of black, okay? And notice that the intensity dipped down there. So the graph corresponds to kind of the visual spectra down here. Over here, I mentioned that these are actually kind of spikes or emission lines. Notice that with those emission lines, what happened to the intensity? It spiked up. So And oftentimes, apparently, that from the same object, the same celestial object, you can get a multiple, you can get a combination of Kirchhoff's laws. So for instance, this part right here where you don't see any lines on the spectra one way or the other, and you can kind of see the graph is pretty smooth, that's Kirchhoff's first law. Then over here, I mentioned you can kind of see, if you can't see it down here in the visual spectra, you can see it up here on the graph, where we have peaks in the intensity at those particular short wavelengths. So now what's happening is that electrons that have been excited are falling back down to the ground state, and they're emitting energy at those discrete wavelengths. Okay, so those are bright line spectra, emission line spectra. Spectrum, Kirchhoff's second law. And then last but not least, over here we have, whether you're looking at the spectra or whether you're looking at the graph, you can kind of see where certain energies have been absorbed and it made it dark, or certain energies have been absorbed. You can see the intensity dip down. Those are absorption lines, and they are occurring because electrons are being excited, and as they're excited, or they're excited by a certain discrete, specific to what is absorbing it, the specific energies, specific wavelengths. It's kind of like, you know how we use DNA to kind of match up with people? Well, we can use spectra or spectral lines to kind of match up what elements or compounds are up there. Now these are pretty good, so I'm going to go ahead and pull them up. Again, if you have Mastering Astronomy, I'd suggest you kind of take a look at these, kind of play around. But this you might recognize, we have both the visual spectra and kind of the graph spectrum. And the way this little animation works is we can look at different objects. So for instance, this is the sun. This would be like a continuous spectrum. Although, if we use a magnifying glass, we can see those dark lines that I showed you as the opening photo of Chapter 5. Well, what if we looked at the energy being emitted by a toaster oven? Now notice that we see it's continuous again, doesn't look like, but it's shifted over here to the long wavelengths. So you can kind of see here visually, this is the graph of this information. Well, if you've gazed at a neon light bulb, neon is a gas in the light bulb, and we use electricity to excite those electrons about the nucleus of those neon atoms, and then as those electrons fall back down to their ground state, this is what they give us. So what appears probably as kind of orangish, that sort of thing, is actually all these little colors coming at us. So definitely we have emission lines that are created by that neon lamp. Isn't that cool? All right, so when we look at celestial objects, one of the things we study are stars. This is a star called Spica. Remember, we talked about actually the Big Dipper. Oftentimes you can use to find the star Spica. You use the handle in the Big Dipper to Arcturus, and the star called Arcturus, and then you can speed on to the star called Spica. Anyway, the color tends to be blue. Stars are different colors, but it tends to be blue, which means it's kind of hot. It is an O-type star, which is actually the most massive type of star. So that's Spica, and this is the visual spectrum, and this is a graph of the spectrum. If you compare this back to the toaster oven, okay, there's the toaster oven. Notice it peaks at the long wavelengths, red. Look at this hot star. Now, one of the things is if we continued this visual spectrum, I guess we couldn't do visual spectrum, but we can continue this plot of this graph to shorter wavelengths. What we would see is actually it peaks over here in the ultraviolet. Okay. So that's the star, and this is a green leaf. Now this is an example of, if the leaf is green, that means we said that that green is being reflected or scattered and all other colors are being absorbed. So that's kind of what we see here, where the green is being reflected. It's what we see, and the other colors are mostly being absorbed. Let's see, I kind of wanted to show you the... All right, so the way this works is it's showing you Kirchhoff's 3 laws, the continuous spectrum, the emission line spectrum, and the absorption line spectrum, corresponding to his first, second, and third law, respectively. Later on in context of a star, perhaps. So, for instance, this is a light source, and notice we get there are no spectral lines, okay, in this particular emission. Let's go on to then emission line spectra. So this represents a blob of what we call rarefied gas. So it's hot, and the heat has, and what we say sparse, so it's not very dense, and the electrons are being excited, and as they fall back from their excited state back down to their ground state, they are emitting light at these various wavelengths. So let's see, choose gas, that's hydrogen, and of course we looked at neon before. All right, so that's emission lines. Now absorption lines, how we get absorption lines is we have that blob of gas that's not rarefied now, or not heated necessarily. We have that blob of gas that is basically, I should say, on the other side of that blob of gas, in sight, in the line of sight, we have an emission source. So the emission source is sending a continuous spectrum to make it available to the gas here that's minding its own business. What that gas will do is the electrons that are around the atoms in that gas will rob particular colors, particular wavelengths of light, and it will go ahead and excite its electrons. Okay, so that creates the absorption spectra, or the dark line spectra. So down here, of course, is kind of a nice, clean, graphical indication of the absorption at those particular wavelengths. That's characteristic of this gas, right? So, all right, so this is kind of just to reinforce this idea of a continuous spectrum. Okay, continuous spectrum, Kirchhoff's first law. Emission line spectrum. Again, we have a hot gas, we have a cloud of gas, and electrons have been excited, and as those electrons fall back down, they emit light at wavelengths that are characteristic of the atoms that the electrons were excited. The atoms about which the electrons that were excited are hanging around. Okay, this is Kirchhoff's second law. Kirchhoff's third law, just put this whole thing up here. Kirchhoff's third law are those dark line spectra, or absorption line spectrum. And in this case, like I said, in this case, the absorption occurs because we have a cloud of gas here where the electrons that aren't excited are actually robbing certain wavelengths of light from a continuous source behind it. Okay, and then what happens is, instead of seeing a continuous spectrum, when we look at the spectrum of that continuous source, we see missing wavelengths, and that's characteristic of the gas. That the gas with the electrons around the nucleus that were excited and robbed that energy.